welcome to Unit 6, our last unit this year, and Unit 6 will be a kind of short unit, although we're talking about some really exciting and important things. We're going to look at matter and energy. We're going to start by looking at thermodynamics, the study of energy and how that energy is transferred. Here are some terms that we're going to encounter as we look at thermodynamics. The second half of the unit will be nuclear chemistry. We will look briefly at different nuclear transformations, fusion, fission, radioactivity, and different applications for those. So let's get started with section 6.1, energy and heat. We're going to look at different kinds of energy, potential and kinetic. We're going to remember conservation of energy, that energy is conserved. We're going to look at work, temperature and heat, and how those different things are related. And last, what a state function is. So let's look at energy. You guys all know this from science, potential energy versus kinetic energy. Remember, kinetic energy equals 1/2 mv squared. We have mass and velocity right here. Kinetic energy is that energy of motion when things are happening, things are moving, kind of like this bicycle here. The bicycle is moving up. It's experiencing kinetic energy. Here I'm going down, experiencing kinetic energy. Right here, it has that potential energy. And that is the energy due to position or composition. You can think of this in terms of water behind a dam or chemicals. In the chemical bonds, potential energy is stored in those bonds before that energy breaks out and we get kinetic things happening, the energy of motion. So let's just remember, we've talked about this before and we're going to talk about it again, but laws of thermodynamics. The first law of thermodynamics states that the energy of the universe is constant. It doesn't get created, it doesn't get destroyed. In other words, we have conservation of energy. Just like all year long, we've been talking about the conservation of matter. We can't create atoms out of thin air or destroy them and they just no longer exist. That's why we balance chemical equations. So, conservation of energy, the same idea. Energy before has to equal the total energy after. Energy just gets transformed. Now let's look at the concept of work. What is work? You might think when someone says the word work of men at work here. Here's a little sign, they're working hard digging things. Or this person thinks she's working really hard. Well, she in fact isn't doing any work at all because work equals force times distance. So, unless there is a force being applied over a distance, no work is being done. Here is an example of someone who might think they're working really hard, exerting a lot of energy anyway, but you know what? They're doing no work. They might be applying a tremendous amount of force to this stationary brick wall, but the wall isn't moving. Therefore, no work is being done in this situation. Now let's look at a couple more definitions we need to get out of the way. Temperature versus heat. And you've probably all studied this before, but it's a good review. What is temperature? Here's an example of low temperature. Low movement. The molecules or the little dashes are showing there isn't very much movement to the molecules. Here is high movement. That equals high temperature. And here we have our definition right here. Temperature equals the average kinetic energy of all the molecules. So if we take the kinetic energy of all these molecules, average that together, that is temperature. So what is heat? Heat is the total internal energy of all of the molecules added together. So here we have a picture of different molecules kind of moving randomly, and usually there is a variety of velocities at which those molecules are moving. They're not usually all uniform. And if I asked you what the temperature was, it's very different from what the heat is. The temperature is the average kinetic energy of all the molecules. The heat is the total, the sum of all of the internal energy of all of those molecules added together. So that is a really important difference between temperature and heat. Can you have some two liquids that have the same temperature but different heat content? Yes, you can. It would be obvious that this one would have, if these were the same, indeed the same temperature, this one would have much greater heat content than this one, because remember, heat is the total internal energy added together, and temperature is only the average. So how are all of these ideas related? We've talked about energy, heat, work. How are energy, heat, and work related? If you'll take a look at this diagram, I love diagrams because if pictures are worth 1,000 words, diagrams certainly are, and so are graphs. They're a lot easier to understand things. So here we have a system that energy is being transferred in the form of heat. If we put energy into this system and we're transferring that energy, and we think about heat. Heat is, remember, the sum of all of the kinetic energy of all of those molecules, all of the internal energy added together. We're adding all of that internal energy up. Here, we have energy transfer in the form of work. If we put energy in, remember that in order for work to be done, if there isn't a distance being moved, if we cannot say force exerted times a distance being covered, then we've accomplished no work. So unless we go somewhere over a distance, work is not being accomplished. So these are just a way of thinking about those in two different ways. Another way we're going to relate these, let's look at a couple more definitions before we can relate work and heat in our system. Let's look at system versus surroundings, first of all. It's pretty obvious. If we have a system right here, and we have the surroundings right here, the system is basically the part of the universe that we're interested in and that we're talking about. That's the system. The surroundings is everything else. Let's look a little bit at this. Triangle is actually not a triangle. It's called a delta. It's a letter in the Greek alphabet. Call it delta, and it means change in. Anytime you see delta and some variable after it, it means change in whatever that variable represents. Q, the lowercase q, represents heat in any equation, or anytime you see that little q means heat, and the lowercase w represents work. So knowing that, if we look at this system, here's our system. The part of the universe that we're considering and thinking about, surroundings or everything else. If we look at this system, and the change in the energy of the system is positive because we're putting work in. This arrow represents work that is being put into the system. Therefore, the delta E for energy of the system is going to be positive. Likewise, if we put heat into our system right here, the change in the energy of that system is going to be positive. It will be increasing in energy. Likewise, if we take heat out, if we remove heat, if we remove that little Q from our system, wow, this is a really big typo. Okay, it should say the delta for the energy in that system, the change in the energy is negative for the system. Pulled this off the internet, and that is a very big mistake on this chart, on this figure. So if we remove heat from the system, the change in energy for that system would be negative. Likewise, if we remove work from that system, the change in energy for that system is negative. Now, this should be a really easy step for you. Can you identify the endothermic and exothermic processes? So let's relate all of this to exothermic and endothermic. We've talked about those before. So remember, exothermic and endothermic, they have to do with thermic, heat. It's all about heat. So when we put heat into our system, it's endothermic. If heat is being given off from the system, it is exothermic. There's another way to think about it on a graph. What if we graph the heat of the system? The heat is in little q, and here's the progression of a reaction, and we start with some reactants. And those reactants have a certain amount of energy, And let's say, remember activation energy, they get over that activation energy barrier and produce some products down here. This is exothermic. This reaction is endothermic. Why? Because right here, the change in heat is negative. It's going from reactants to products. It's going from a higher energy to a lower energy, giving off heat. Here, we're going from a lower energy to a higher energy, and the change in heat is positive. Once again, when that change in heat is negative, when heat is being given off, it is exothermic, energy is given off. When we are taking heat in, it is endothermic, energy is being absorbed by the system. And that brings us to the idea of a state function. And if you've never heard this term before, it's a pretty simple idea. A state function is when a property or a function changes independent of the pathway. It doesn't matter how it got there, it's independent of that. And I'm going to give you an example because it's a lot easier to see by example. Elevation change is a state function. It's a property that changes independent of the pathway. Let's look at our little car here in our carport. This car can go, let's say there's just straight up. Let's say there's a little elevator here and it goes straight up and ends here. Or this little car could drive over here, come up the ramp, around, take this path around, and then park here. Does it matter how it got from here to here? That's the elevation change. When it changed elevation, it went from this elevation to this elevation. Does it matter if it took pathway A or this other pathway? The elevation change remains the same regardless of how it got there, regardless of the pathway it needed to take to get there. Now, an example of something that is not a state function would be the distance traveled. That would be a property that definitely depends on the pathway. If we're talking about the distance that we travel, it's going to be a big difference between here and here, pathway A, or this other pathway, right? This will be a very long distance traveled. So when we talk about state functions, energy is a state function. It doesn't really matter how it gets the energy. It will arrive at that energy regardless. Let's take the example of potential energy, and maybe the pathway is very bumpy, and the pathway all up the hill is bumpy, or it's smooth. Will that affect the ultimate amount of potential energy that is obtained at this position on the hill? No, the energy would be the same either way. A property that depends on the pathway that we've been talking about would be the way the energy is distributed as heat, and it should say or work, not of, or. Heat or work would be the distribution of that energy. The heat and the work are not state functions because they definitely depend on the pathway. Heat is considering the total internal energy all added up together. The work is the force times the distance. Those definitely are dependent on the pathway and how we get there. Energy is not, so energy is a state function. Points to remember. Energy. What is potential energy? Kinetic energy. Conservation of energy. Definition of energy. I don't think I actually said that before. Let me pause that and write that down. Ability to produce work, or to do work, or produce heat. There's what energy is. We looked at potential, kinetic energy. Work. What was work? Force over a distance. Temperature versus heat, the difference between those. We talked about how energy, heat, and work are related, and what a state function is, and which one of these things are state functions and which ones are not. So here's another, a little advanced idea for you if you're interested in doing more work, or if you come up with something on your own. This is a huge topic. We'll cover a lot of this in much more in depth in physics, but we just needed to give you some quick definitions so that we can start this unit on matter and energy. So look forward to seeing you in class.